the hall. Those are the two places where they can be. So if you have a jacket, those are the two places it can be. Okay? So, Caden, in your backpack, please. Okay? Again, I don't want you to bring them. It's only going to get colder. You're going to bring bigger and bigger jackets, and they're going to stay in your locker. Okay? Or you can fit them in your backpack. Your choice. Up to you 100%. All right, ladies and gentlemen, what is the coolest thing that you did over break? Slow down, people. Slow down. I cannot keep up if you're going to do that. You need a charger. You got a Dodge Charger? Oh.
I spent my time in the car.
You spent your time in the car. You traveled the whole time or what?
Basically.
What do you mean basically? You never stopped?
Twice, and then I went all the way to Chicago and back.
Chicago and back, that's like a 3-hour ride.
I know, but like it's long. And then Madison like 3 times.
Madison? Why did you go to Madison 3 times?
I got family down there.
And you couldn't visit them all at once? They each had a different day for you or what?
Not.
Wow. That's
It
just,
sucked.
that's, okay. Okay. All right, who got a gift they had to return for Christmas? Tell me it wasn't a car ride.
It was too big.
It was too
I
big?
got pants, but they're too big. So I
You got
returned.
pants, but they were too big. Who were they from?
My uncle.
Okay. All right. All right. Anybody else gift you had to return? How about a terrible gift?
Yes.
Yeah.
Okay. Josie?
I have a friend who recently got a job in the mall, and he was like, I'll pick something out for you at my work, which is just like a clothing store. And I was like, all right, but you don't know what I like or what I wear. And he's like, it's okay, I'll figure it out. And he got me the fuggliest shirt I've ever seen in my life, and I didn't have the heart to tell him that I didn't like it. So I was just like, thanks.
So when are you going to have to wear this when you go somewhere with that friend?
Gee, I don't know. And I can't even return it because he works there.
It doesn't work there every day.
So most days. So
What you do is you make arrangements to meet him somewhere, and then you ditch him and
Yeah.
go return it while he's meeting you in that spot.
or I'll just like
Creative.
sell it on Facebook. So yeah, sell it. Do you want it?
Do I want it? Josie, I don't think you and I wear the same size clothes.
But that's okay.
So,
But it was pretty interesting.
Phoebe, you had a terrible gift?
Yes, my grandpa framed a picture of my car crash and gave it to me.
Really? That's a nice reminder. In case you forgot how much you smashed up your car,
It was in a ditch.
it was in a ditch.
Yes, and then he put Phoebe's lawnmower like as a label on it because I took out a bunch of weeds going down, so it was like a path.
How did you
How
do
have
that?
we not heard this story before,
I
Phoebe?
hydroplaned going onto the highway, like I spun out of control, went down a hill into a ditch next to the highway.
How did you like not die?
I don't know. I was afraid I was gonna go into the highway and the car was just gonna hit me. But it was really traumatic. And now
Really
it's-
traumatic, and now you
it's
have
framed in my
now
room.
you have a framed reminder of it every day in your room. Okay. Anybody else?
What's he looking at?
All right. Yes. You went fishing 3 times.
Did you get your
Ice or on the water? Well, let me rephrase that. Solid or liquid water? Liquid. Okay. There were a lot of people who were out fishing when they
Was it a
used
good
those.
fish finder? I didn't forget.
My son got one of those too. So
What'd you get for Christmas?
Cat fit.
New fit.
what?
The new fit.
Pants and a shirt.
That's it? That's also a
I
rug.
got other stuff too. Got a radio from my garage, so I'm good to go.
There you go.
There you go. There you go. All right, ladies and gentlemen, open your computers up and get to your EISN. Okay? You need a charger. Then you can
I remember the first time I ice skated.
Well, ladies and gentlemen, it may not seem like it. 2 months from today, on March the 2nd, actually 4th, on March the 4th, which would be a Monday because the 2nd would be a Saturday, you will be done with the second trimester of classes here at East. So there is not a lot of time left, okay? Also, not next week, but the week after, it's a 3-day week. The week after that, it's a 4-day week for you. And then a week or two after that, it's like a 4.5-day week for you. So you got lots of time off coming, ladies and gentlemen, okay? So we do have a bunch of things to do. When we left you before break, ladies and gentlemen, and I don't mean that Friday when we made suckers, but before that, we were talking about gas laws. And the first gas law we covered was Boyle's Law. Now remind me, what two variables are involved in Boyle's Law? Volume is one of them. What else? Pressure. Okay? So if we increase the volume, ladies and gentlemen, what will happen to the pressure? If we increase the volume, it'll go down. It'll decrease. Okay? What happens to temperature? Temperature is a constant. It stays the same. What about the amount of gas? Stays the same. Okay? I would know that for your quiz on Friday. Okay? I would know that what is happening to those variables for your quiz on Friday, just so you know, ladies and gentlemen. Okay? So Boyle's Law was the first. Boyle's Law also is the only gas law that has an inverse relationship in it. The other gas laws that we're going to talk about are all direct relationships. Christopher, what does it mean to be in a direct relationship? It is a 71-minute class, Chris.
And the variable changes and the other one goes the same direction.
Okay, so if one variable changes, the other one goes in the same direction. That's what a direct relationship is. Unlike Boyle's Law, which is an inverse relationship, where what happens, Stephen?
One variable increases while the other decreases.
Okay, very good. Those are the only two choices. If you're talking about two variables, the only way they could change is to increase or decrease. The only way the other one could change is to increase or decrease. So they're either both going in the same direction, meaning they could both be increasing or both be decreasing. Doesn't matter, that's still the same direction. Or they can be going in opposite directions. Opposite directions is an inverse relationship. Same direction is a direct relationship, ladies and gentlemen. So today, we're going to start looking at two more gas laws. We're going to start looking at Charles and Gay-Lussac's laws. So, ladies and gentlemen, in your notes, you need to get to slide number 28, please. 28. Your dad was Charles?
Yeah.
Really?
Yeah.
Cool. So if your dad is Charles, why do you have a different last name?
I have a different mom.
Oh, you took your mom's last name?
My mom's on.
Okay. Okay, that makes perfect sense. Because this Charles Law is the last name, not the first, by the way.
Oh.
Okay? This Charles Law is the last name by the first. Okay, so if we think about it, there are four variables, right? That affect the gas. What are they? Temperature, pressure, volume, amount of gas. We've already covered pressure and volume, correct? Okay, so Charles' Law has to deal with some different things, okay? Charles' Law deals with volume, okay, and temperature at a constant pressure. Now, we actually see Charles' Law in winter in Wisconsin. When? Anyone here have a birthday in the next 2 to 3 months? Guarantee you someone has experienced Charles' Law for your birthday. Can someone explain how?
We were born in the cold.
Okay, but again, you're probably not affected by pressure and volume as much because we are solid objects. So we need something that is a gas that when we change its temperature, its volume will also change.
No, wait.
Is it when a balloon deflates in the cold?
Thank you. So if you buy Morgan a balloon for her birthday, you go get it at the store, you take it outside and put it in your car. As you're driving, that balloon will deflate. Why? Now think about our 4 variables. What happens to the Morgan's birthday is in when?
March 1st.
March 1st. We're ending the trimester on your birthday.
I know.
Happy birthday. So what is it about Wisconsin at this time of the year that would affect the balloon?
It's cold.
It's cold. So we're talking about temperature doing what? Decreasing. So what happens to the balloon when you take it out of the store and you're riding home in your car?
The volume decreases too.
Why?
Because it's a direct relationship.
Okay, and temperature went down, volume went down, proving that it is a direct relationship. What happens when you get to inside the house or you deliver the balloon to Morgan in her home and it warms up again?
It'll inflate.
It'll go back to inflating to its regular size. Go back to inflating to its regular size. Mr. Brennan? Yes, I do. Would you like him? Excellent. Okay, you can, if you want him for the whole day, and the rest of the week, you're welcome. No, let's start with today and we'll negotiate. Okay, all right. All right, sounds good. Bye. Angel, you're out of here. Yes.
What do you do? Hiciste.
With any luck, maybe it'll be for the whole week, Angel. I tried. Okay. So, just like Boyle's law, 2 variables, pressure and volume. One goes up, one goes down, inverse relationship. Charles' law also, hey, you gonna put it back in my calculator or are you just gonna leave it there? Hey, angle. Bye. Some things never change. There is a relationship between 2 variables in Charles' law. Okay? His law relates volume and temperature, but they're in a direct relationship, not an inverse, which means if temperature goes down, what happens to volume?
It also goes down.
It also goes down. If temperature goes up, what happens to volume?
It goes up.
It goes up as well. Now let's think about this for a minute. Let's go back to visualizing something we did earlier in this unit. The idea that a ping pong ball hits that wall, bounces off it, hits that wall, and just constantly bounces back and forth. That ping pong ball creates pressure by how many times or how often it hits the walls of this container, correct? So what does changing the temperature actually do to that metaphoric ping pong ball?
It speeds it up or slows it down.
Speeds it up or slows it down. However, we don't want it to hit the walls more or less often, because otherwise we would be changing the what? The pressure. So we have this ping pong ball, hits that wall, bounces over, hits that wall, bounces back. Once every second. But now we decrease the temperature. That means the ping pong ball is going to move slower. So obviously it can't make it all the way across the room in the same amount of time if it's moving slower, correct? So what is the other adjustment that is made so that we do not change the pressure? The walls would have to what? If the ball is moving slower.
Spread apart.
If the walls go further apart,
It's gonna take more time.
it's going to take more time. And we already just slowed it down. So So the walls have to move closer together. That's that idea of that direct relationship. If we want the ping pong ball to hit the wall once every second, but we're slowing it down, the walls have to come closer. It can't travel the same distance in that same amount of time because it's going slower. That is temperature's part of it. By the way, temperature would have to be in what unit?
Kelvin.
Temperature is going to have to be in Kelvin in these calculations. Why? Because we cannot have temperature become the negative, because what would happen to volume then?
Not there.
It would have to be
0?
negative.
Negative, yeah.
Can volume ever be negative?
No.
So we can't have volume ever go negative, so we can't have temperature go negative either. Okay? Now, pressure and amount of gas are still held constant. Just like we did with Boyle's law, we held temperature and amount of gas constant. Now we're holding pressure and amount of gas constant. Okay? Now we're holding those two constant. All right? So, again, we have a formula for this, and we get what we call a constant, a K value. The difference is now, when we had pressure and volume, what did we do to them mathematically? What did we do to them mathematically because they were in an inverse relationship? Are we guessing or are we sure on that one? Because you kind of faded off at the end. It was like, divide.
I'm guessing.
Boyle's law. What do we do with P and B? P1, V1, what do we do with them? What? We multiply them. That is an inverse relationship. What are we going to do here in a direct?
Divide.
We're going to divide. We're going to divide. So we're going to have V over T equals a constant. Volume over temperature equals a constant. Okay? Assuming we don't change what two things?
Amount of gas and pressure.
The amount of gas and pressure. Okay? The amount of gas and pressure. What that means is if we know a volume and a temperature, we can predict any new volume and any new temperature that we want. But our temperatures have to be in, how do we get from Celsius to Kelvin?
Subtract
273.
What do we do, Shenta?
273.
Well, good, that's a number.
Yeah.
We do 273, Mr. Brand.
Yeah.
Do what with it?
So, Kelvin to Celsius, Celsius to Kelvin.
Celsius to Kelvin.
Oh, plus 273.
Plus 273. Plus 273. Okay? So these two numbers down here, ladies and gentlemen, have to be in Kelvin, and they have to be, okay, positive numbers in the end. She lied.
It was the wrong kid.
Believe me, there's only one of you, Engel. Okay, we don't get you confused. All right. By the way, if you flip this over, you would still have a relationship and it would still create a constant. Okay? It would still create a constant. But where was V in Boyle's law? It was on the top. We multiplied P times V. So we want to keep it in that same place here, ladies and gentlemen. That's why we do V1 over T1. You would get a constant if you did T1 over V1. You would. Okay? But we want pressure and volume always to be on top of our calculations, which means temperature is always going to be good on the bottom. Yes, excellent. I'm glad you could see that here, that it's on the bottom of these. Good, excellent, wonderful. Yeah.
Wait, can we watch this?
No, they're in your thing. If you want to watch them, go ahead. All right. So here's what it would look like if we collected some data, ladies and gentlemen. Okay? Now, there is a fact online that you can go and you can play with, ladies and gentlemen. This is what it looks like. If you click on that link that's in your notes, it takes you to this. This is, you're going to use ideal gas law. Ideal means we're going to get things to work out the way we hope they would. Those assumptions that we made earlier, that gases do not attract or repel each other, that they're moving in straight lines until they hit something and then they bounce off. All of those things are part of this, what is called ideal gas. Now with this thing, with this this simulation, you could take and add a gas. So if we hit the pump here, we put gas particles in there. Okay? Now, those represent, again, the gas particles, and you'll notice they hit the wall and they start bouncing off and they're moving in straight lines. They're hitting each other. And we put in enough gas to where we have a pressure of 14.8. It's moving around a little bit, but whatever. We've got a pressure. Here's our temperature up here, ladies and gentlemen. Now, according to the law that we're talking about, what is held constant? What don't we want to change? Nope, we can change temperature. We cannot change what? The amount and the nope. Okay, good. We were down to 1. Okay? We cannot change pressure. So I am going to take and I am going to hold the pressure constant, allowing the temperature to move up and down. So I click on this bottom one. And now, ladies and gentlemen, if we take this handle here and we slide it, what am I doing to the volume of this container? Decreasing it. Now, the temperature is 300 Kelvin right now. Do you see that up at the top? So if I make this smaller, what should happen to that temperature? Should decrease. We're making one smaller, the other has to get smaller. They're in a direct relationship. Okay? They slow down so that they don't move as fast, thus not hitting the walls of the container as often. Why? Because the walls are now closer together. Our pressure didn't change. Our temperature did. Went from 300 Kelvin down to 173 Kelvin. Okay? Now, again, when you're playing with this, there are some other things you can do. You could take and you could make it bigger. So now, our temperature has gone up from the original 300 because our container has gotten bigger, even though our pressure is not changing. So it's kind of a cool fact. It lets you actually see the particles as they're moving around. I believe even there's a way you could change the type of particles if you wanted, heavy or light, okay? Now, what if we change from a heavy particle to a light particle? What would that do? Now, again, if we change from a heavy to a light, we wouldn't want the temperature to change right now, correct? But if we use the lighter particles, what would that mean for those particles? At the same temperature. They would move faster. Thank you. Good. Because remember, temperature is dependent on the mass, and it's dependent on the speed or velocity. So if we had gone to a lighter particle in here instead of a heavier, they would have to move around faster, okay, to be at the same temperature. Again, things that you can play with, things that you can do, ladies and gentlemen. Okay? So, again, you could change things. So now, did you go down to the career center?
No.
Where did you go?
Attendance. And you didn't say
He went to the wrong spot. I will send him back to you. He's bringing it. He's taking everything he's got. Don't send him back. Thank you. Bye. Career Center. Why would you go to attendance? Nobody there wants you.
You didn't say where.
You didn't ask, apparently.
Because I thought that you were going to tell me.
Ah.
Oh. All right.
They had the
Goodbye. Goodbye. Okay. So anyway, ladies and gentlemen, kind of a cool visual. You could take and you could heat it up. Shows you how the container would have to expand because we're heating it. Yeah, shut up. Cool it down. Container is going to have to get smaller. Oops, sorry, it's letting the pressure change. Don't want to do that. Cool it down. The container is going to have to get smaller. Okay, different ways of you foreseeing what's happening here. Smaller particles if you want, or putting more different particles in, all kinds of stuff to use. All right, great, awesome, excellent, ladies and gentlemen. But what do you notice about the lines we get? Both straight lines, indicating what? Constant relationship. Indicating a constant relationship. Okay? Indicating a constant relationship. Notice the temperature, though. Kelvin here. Okay? Kelvin here, and again, volume over on this axis. Okay? So, we get two similar formulas, even if we were to do it in Celsius, as long as we, again, are doing it in Celsius, we're still going to get a semi-decent relationship. It isn't going to be as good. Okay? Straight lines, though, meaning that something is in a constant relationship. In this case, volume and temperature. Okay? So we got that. All right. So, if 32 liters of helium gas is at room temperature, 20 degrees Celsius, and that volume, what volume would the same gas occupy if its temperature were increased to 85.3? Now be careful. It says increased to 85.3. That would be different than increased by 85.3 degrees Celsius. If we said it was increased by 85.3 degrees Celsius, we would have to add this number to the original one. It says it's increased to. Language is important. We could talk about changing the temperature by a certain amount or to a certain amount. When you read your question, make sure you understand which is happening. Okay? And we're going to assume there is no change in pressure, ladies and gentlemen. So, we're going to use V1 T1 equal to V2 T2. Again, I don't care which conditions you put into which side. It doesn't matter. But this volume goes with this temperature. And they got to go on one side or the other, ladies and gentlemen. And also, what do we need to do to temperatures here?
Convert to Kelvin.
Convert to Kelvin. So the first thing I'm going to do is take 20 degrees and convert it into Kelvin. Add 273 to it, get 293 Kelvin. I'm going to take my 85.3, I'm going to... Yes. What? You're kidding. You're kidding. Keep him anyway. Don't send him back, please. We've been through this. The class gets all excited, then he comes back and then they're about... Oh. Thanks. Bye. Okay, everybody, let's go next door. No? All right. So, we're going to put those two temperatures in the bottom here. This volume we're going to put in the top. Now, here's the difference between what we did before and this time. Our setup is different, but the math is still the same. We need to do what with V2? To solve this problem, what do we need to do to it? Don't everyone jump on this all at once. I know you had a week off. Some of you haven't had math class today, and I know you forget everything as soon as you leave school in math. But what do we do to solve for V2? What do we got to do?
Times 300, the bottom number.
The bottom number.
The red bottom number.
The red bottom number.
Yeah.
As opposed to the other red bottom number.
Yeah, the red one.
Okay. Number one, we could do cross products are equal. Correct? We could do cross products are equal. Okay? And if you have to do that, that's not a bad way of going about this. We could take cross products and set them equal to each other, or we could simply multiply by 358.3. Why? To isolate a variable. To get it alone on one side to solve for it. So when we multiply this side by 358.3, we do the same to the other side. So we take 32.3 times 358.3 Kelvin, and we divide it by 293 Kelvin. What happens to our unit of Kelvin here? Cancel. They cancel. Now, temperature has to be in Kelvin. Volume, I don't care what unit it's in. I don't care what unit it's in as long as they're the same on each side. Temperature, it isn't just that they're the same on each side. You cannot do this problem in Celsius. You cannot. You have to do it in Kelvin. So our V2, ladies and gentlemen, becomes 39.5 liters. 39.5 liters. Question. You guys are exciting today. Exciting today. Get a calculator out, ladies and gentlemen. Get a calculator out. All right. Just so you see, ladies and gentlemen, if we use Celsius, we'd get 32.3 liters times 85.3 degrees Celsius divided by 20.0 degrees Celsius equals V2. Somebody do the math on this for me and tell me what we would get. Now remember, our original answer over here was 39.5, correct? If we work this problem in Celsius, tell me what we get. Let's go. $32.3 times 85.3 divided by 20.
137.8. You rounded.
Yeah. Big difference, huh? 137.8 versus 39.5. That's because this temperature went up by over 4 times. These temperatures did not go up by 4 times. That is the other reason we have to do these problems in Kelvin. Celsius, the changes are too dramatic. It doesn't hold. So we have to do these in Kelvin for the calculation. All right. If 612 milliliters of nitrogen gas is at a temperature of 125 degrees Celsius, what would the new temperature be if the volume was lowered to 456 milliliters? Eric, tell me what's going to happen to our temperature here.
Temperature is resort to it decrease
Why?
because volume is decreasing.
Good. So we have an idea already that our temperature should decrease. Final answer needs to be what, Joshua? Less than what? Nope. Less than what, Maddie?
125.
Less than 125. Why 125 and not 612, Josh? Well, we are changing the volume. I want to know what's going to happen to the temperature. Now, Eric said it's going to get less. Now, Celsius or Kelvin, doesn't matter. It's going to be less than this number in the end. Okay? Now, we have to do the problem in Kelvin, but either way, if the temperature is going down, it goes down in Kelvin, it goes down in Celsius. Either way. Okay? We can't do the calculation in Celsius, but we can make the prediction in Celsius. Okay? So again, we're going to use Charles' law. V1 over T1 equals V2 over T2. We're going to convert our temps. We're going to take the 125, add 273, that makes it 398. Now, this problem we have to be careful about one thing, and that is this. Where is T at in this equation? On the bottom. We have to be careful not to solve for T and actually be finding the reciprocal 1 over t. So even when these numbers are here, ladies and gentlemen, I need to solve for t, but I need it also where? I need it on the top. Now, the one thing you can do to these problems that you can always do that will guarantee you get that t on the top, ladies and gentlemen, is we can do cross products are equal. So we can do 612 milliliters times T2 equal to 456 milliliters times 398 Kelvin. By the way, I don't care if you like to use time signs or if you simply like to put them into parentheses. This means that these two will still be what? Multiplied together. I don't care. Okay? You also don't technically have to show me this step in a problem. Once you've done this, you can solve for it. Just solve for t and show me what you get. You don't have to show me this. This is an intermediate step. I don't need to see this. But if you need to do this so that you don't accidentally solve for the reciprocal of t, do it. Okay? By the way, this is also the reason that I asked Eric what's going to happen to t. And you said what?
It decreases.
Okay. If you solve for the reciprocal of t, it will increase. If you accidentally think you're solving for t and your temperature goes up, I guarantee you solve for the reciprocal of it. Okay? That's the only way it can go up. Now we solve this, ladies and gentlemen. Now we solve this. Okay? Again, I took what I just did and did the cross products. Now isolated t, this is what you get. But you'll notice this has flipped over here and we're multiplying by this as well. Why? Because that's what happened when we got t over onto the other side. Okay? Questions? Okay, we solve it. We get a temperature of 296. But what do we need to do to this yet? We need to go back into Celsius. Now, again, this particular problem didn't tell you you had to. If you left it here, absolutely fine. It doesn't say that you have to go back into Celsius. A lot of times I will tell you that. I want the answer in Celsius. I didn't on this problem. So if you left this here, that would be fine. But what do you notice about these numbers? This is what? It is still a smaller temperature that we now have in Kelvin, even compared to what the original temperature was. Our temperature went down like Eric said it would. When we go back into Celsius, ladies and gentlemen, we take that 296 minus 273, whoops, and we get a temperature of 23 degrees in Celsius. It had gone down in either one. Questions? Yes, no, maybe so. All right. Oxygen gas is at a temperature of 52.3 degrees Celsius and has a volume of 15.3 liters. What would the new volume be if the temperature was changed to 290.2 Kelvin, assuming no change in pressure? What is the only thing that makes this problem a little bit more difficult? May make it more difficult. Some may say it made it easier.
You have to convert it to see if you have to go up or down.
What's that?
You have to convert to Kelvin or Fahrenheit.
Okay. I gave you different units. I did this to you at the end of the Boyle's Law too, right? Pressure in one unit, pressure in a different unit in the second time. I don't care which one you pick, but we got to get to the same unit. But with temperature, we always have to be in
Kelvin.
Okay, so what is this temperature in Kelvin, ladies and gentlemen? Anybody?
325.
325 point what? Okay, so now that we know that, what is actually happening to our temperature here? going down. Achilles, what's going to happen to our volume? So when temperature goes down, volume increases now?
Decrease.
Volume went down. Temperature went down, right? Okay, direct relationship. Temperature's going down. What's going to happen to volume? It's going to decrease as well. Final answer needs to be what? Less than what number? No.
52.3.
15.3, the original volume. This is already going down. We know this. It's going to this. Final answer has to be less than this number. V1T1 equals V2T2. We're going to convert the 52.3 into Kelvin by adding 273. Now again, when the V is on top, we don't ever have to worry about accidentally solving for the reciprocal. Because it's on top, we won't make that mistake. At least you shouldn't, I hope. But I do need to isolate this variable. So I'm going to multiply this side by 290.2. What I do to one side, I'm going to do to the other. So we get 15.3 times 290.2 divided by 325. Final answer, 13.6 liters. Questions, ladies and gentlemen? Yes, no, maybe so. Okay, you want the good news or you want the bad news? You don't want any news. Okay. But anyway, we got another gas law. That is Gay-Lussac's. Now, good news, Gay-Lussac's is a direct relationship. What are the variables that we are left with? What haven't we worked with yet? Still not working with amount of gas yet. Pressure and temperature. Okay? Pressure and temperature. Still in a direct relationship. Okay? The pressure of a gas will vary directly to its Kelvin temperature at a constant volume. So, what's changing? Pressure and temperature. Direct relationship. What's staying the same? Volume and the amount of gas, the number of moles. P over T. Same exact formula except we're putting pressure over temperature. Still equals a constant. That means P1 times T over T1 is equal to P2 over T2. Same exact formula. Notice, where's T still? Bottom. Where was P in Boyle's law? Where was P in Boyle's law? Did we divide anything in Boyle's law?
No.
So then where is it?
It was in the first part.
Okay, but is it on the top or the bottom of a fraction? It's on the top. P and V and T never change where they are in these formulas. T, if it is involved, is always on the bottom. P, if it is involved, is always on the top. V, if it is involved, is always on the top. We are not going to change that. Hey, look at the graphs. What do you notice?
There's no data.
Okay, look at my graphs, not yours.
Correct.
Direct relationship. Straight lines, which means a constant. Okay? Straight lines, which means a constant, ladies and gentlemen. You want to play around with that, FET? You are welcome to, but here we go. Oxygen gas is at a temperature of 31.5 degrees Celsius and a pressure of 1.35 atmospheres. What would the new pressure be if the temperature of the gas was changed to 69.5? Angle, what is happening to our temperature here?
I don't know.
Well, you got two choices. Increase, I'll give you three. Increasing, decreasing, or stay the same. Look at the numbers. First of all, temperature. What unit is temperature in? What unit is it in, Jack? Either Celsius or Kelvin. So find me the two numbers in Celsius or Kelvin in the problem.
31.5 and 69.5.
So what's happening? Increasing, decreasing, staying the same.
Increasing.
Okay. So, Christopher, if temperature is increasing, what's going to happen to pressure? It's going to increase as well, which means, Josie, our final answer is going to be greater than what? Well, what's the only other number in this entire problem? 1.35. Okay? 1.35. Please save the pieces. What's the unit? ATM. What is ATM the unit for, Faith? Okay, then read the problem and tell me what 1.35 is. Says it's the what of the gas? Two or three words before the number, Faith. Okay, find it. I think it's what, 37? Pressure. So they may tell you in the problem, but again, you should be able to recognize things by units, ladies and gentlemen. ATM, unit of pressure. Milliliters, what's the unit, Jasmine? What's it describing? Milliliters. Pressure, volume, temperature. Volume. MMHG, Irving. Pressure. KPA, Katie. Pressure. Cubic centimeters, Eric.
Volume.
Volume. Degrees Celsius, Achilles. Temperature. Kelvin, Shenza. Temperature. Let the units help you. Let the units help you. Okay? They don't help you if you don't know what they are. Put them at the top of your periodic table. Put them somewhere where you can find them. P1 over T1 equals P2 over T2. Convert our two temperatures, 31.5 into Kelvin by adding 273, 304.5. 69.5 plus 273, 342.5. We can now put everything into our formula. P1, T1. P2, T2. Again, my suggestion would be to put these all on one line. Do cross products are equal. Okay? But you don't have to. Why? If I want to isolate P2, all I need to do is multiply this side by what, Stephen? If I want to isolate P2, if I want to get this variable alone, what do I do to this side? Stephen, your voice is changing dramatically. You're starting to sound like Shenza now. Shenza apparently cannot be patient. So what do we do?
Multiply by 342.5.
And what you do to one side,
You do to the other.
you have to do to the other. In the end, this is what it looks like. P2 is equal to 1.35 times that 300. Whoa. Sorry, these are reversed. Those are reversed, ladies and gentlemen. That's my bad. My bad. Now we'll see if I did the math actually correct. So our temperature went up, right? Correct? So is that a reasonable answer?
Yes.
Why?
Direct.
What?
It's direct.
Okay, and it went up. So while I may have switched those numbers around, I think my answer is still correct. If someone else could check it, that would be wonderful. Otherwise, you're just trusting me. We're good? Okay, thank you. Questions? Air is under a pressure of 896 millimeters of mercury at a temperature of 16.3 degrees Celsius. If the pressure of the gas doubles, what will the new temperature of the gas be? Assuming no changes in volume. What's happening to, what is changing here? Read the problem, what is changing?
Pressure.
Pressure. Up or down? Up. What's got to happen to temperature then? Okay. Now, if pressure is going up, where's the second pressure here?
Double.
Okay, it's doubling, right? Okay, if pressure doubles, what happens to temperature? It has to double as well. In what unit though? In Kelvin. If the pressure is going to double, the temperature is going to double, ladies and gentlemen. We're going to take our 16.3, we're going to convert it into Kelvin, 289.3. We're going to put it into our formula here. Again, this is one where you got to be careful. Do not solve for the reciprocal of temperature. Okay? Do not solve for the reciprocal. I'm going to take it, I'm going to multiply both sides by temperature. I'm going to divide both sides by 896. Going to divide it by this. Brought over onto the other side. So 896 goes on the bottom. 289 goes on the top. Okay? Our temperature had to double. So we went from 289.3 to 579.6. How do I get this in Celsius? Minus 273. 306.6 degrees Celsius. Notice this is not a doubling, is it? No. That's why your relationships have to be worked in Kelvin. Okay? In Kelvin. Questions? Okay. Take out your practice problems, ladies and gentlemen. The second page of your packet and the third page of your packet are all combined or gas laws for Gay-Lussac and Charles. Go to work. If you have questions, call me over. I will be happy to help you out.
Is it this one?
Is it the packet that says Unit 6 gas laws?
Yes.
That's the one I would go with. Does it say Boyle's Law right at the top?
Yeah.
Then I would change the page and go to the one that says Gay-Lussac and Charles.
I think it's.
You're welcome. Boy, Angel, isn't it terrible that nobody wants you today?
I walked in and she was like, "Oh, you gotta take the STAR test." And I told her that I've been passing. And she was like, "Oh, are you Angel Munoz?" I was like, "No." And then she kicked me out.
We have what?
What size?
70.
70? 70? That'd be about yay big.
0.7.
You're welcome.
Gay-Lussac's law.
Gay-Lussac's Law.